So the first equation, this is linear. So y equals mx plus b. You guys would have covered it in grade 9 and probably grade 10 again. M deals with the slope of the line, and b is the y-intercept. So b is, if I have, say, a line like this, the y-intercept here would be the number 2, and then we just kind of find out the rise over the run, and that would give us our m. Does that ring a bell? Yeah? Okay. This is a quadratic equation. A quadratic deals with a parabola when you go to graph it. So it looks roughly like this. You have something that kind of goes like that. Have you seen that before? Yeah. Okay. So when you go to graph them, do you know how to graph like an original one? Have you ever done, I'll take that off. If you were to graph this specific function, do you know how to go about it? Do you know where you would start?
You try to find out what x was.
Okay, so you could do, you could definitely make a table when you're doing it. There's many different ways of graphing things. So you've probably gone through class and they've given you something that looks like this, where they have your input is your x values and your y values. And what you can do is you could put arbitrary numbers in here. So assume that all of these are with the value of 1, okay? Yeah.
We're going to go on.
So assume all of these go for the distance of 1, okay? So we go 1, 2, 3, all the way up to 10. That's how big this graph is. You can put any numbers in the x values. So say we had 0, for instance, okay? I would plug the number 0 into the equation for the x value in terms of graphing it, okay? So we have y is equal to, instead of x, I plug the number 0 in, squared. Okay, do you know what 0 squared is?
0.
Yeah, so you get y is equal to 0. So your coordinate, x at 0 and y is at 0, okay? So that means when I go to plug that in, I find 0 and 0. There's my very first point on this graph. Now say I wanted to find the value along x when it's 1. So there's going to be some point up and down this graph when x is 1. This is when x is 1. I got to find out the y value. So in order to do that, I put the number 1 in for x, and I work on the same idea. I use my y. Y is equal to, I plug the number 1 in for x squared, which is 1. So y is then 1. So my next coordinate is when x is 1, y is 1. Okay? So I go to x1. Does that make sense where I am? And I go up 1. Here's another point. Essentially, I'm going to create several points, and I'm going to connect the dots and make a graph of this. So let's go work backwards too. What if we were at a -1, which would be on this line here? Does that make sense to you? Okay, so if we have -1, I plug it in for my x value. Y equals -1 squared. Do you know what -1 squared is? Yeah, positive, because the negative times the negative is a positive. Good, okay, good. You know that stuff. So our next coordinate is -1 and +1. So here's the next point. Is this making sense?
Yeah.
Does this look familiar, making a table chart like that? Do you want to keep going that way, or do you want me to show you kind of like a faster way of graphing a quadratic?
Faster.
Faster way?
Okay.
Okay.
I know the basics.
You know the basics? Good. Okay, so this is the recording. So with a quadratic, this is the vertex, the lowest point. We're going to get some shape that looks like this, okay? We're going to find out the other points after. I know that isn't perfectly accurate. But the vertex is the lowest or highest point, depending if it's facing up or down, okay? So when I go to graph this, I go over 1, and I square that number. And that tells me how much to go up. So we knew that 1 over 1 squared is 1, so I go up 1. Same with the other way. -1, I went -1 direction. -1 squared is 1. So let's talk about the next point. The next point, from the vertex, I'm going to go over 2 spots. 1, 2. What would 2 squared be?
4.
4. So from here I go up 1, 2, 3, 4. There's my next point on this graph. Okay? Because we're dealing with squaring. That's what's important here. We're constantly plugging numbers in and squaring them. So same with the other direction. If I were to go over -2, what would -2 squared be?
4.
4 again. So you're going to start to notice that this becomes like a mirror image down the middle. Okay? And then what about if I went over to 3? Do you know how many I'd go up?
9.
Yeah, good. And I do the same on the other side. So here's the basic of a quadratic. Okay? So this is your original quadratic, okay? So y equals x squared. Now, in grade 11, you guys are going to work with something called function notation, which is f at x equals x squared. Have you kind of gone into that?
Yes.
Yeah, okay. All that is they've essentially replaced y with this, okay? Now, what this is saying is there's some formula, that's f for the function, and it has the variable x involved in it, okay? It's a way to write a formula and then figure out what numbers we're supposed to plug in. So for instance, sometimes they'll ask you not even to graph something, they'll put the formula down like this. They'll tell us what the parent formula is. F at x is equal to x squared, okay? And then they may tell you f at 3, okay? Have you seen anything like that before?
We had it.
What would you have to do with that?
We'd fill in 3 as x.
Yeah, exactly. So what would f at 3 be equal to? Good. That's simple? Makes sense? Okay. Let's see how far they've taken you with this stuff. What you're going to eventually, now every book is different, so I'm just going to use arbitrary ones. A, F, B, minus, maybe it's H plus K. Have you ever seen anything, and I'll color code these for you actually.
Yeah, I've seen.
You've seen that? Ah, okay, good. So that means you definitely got into this stuff. Now, do they use those variables, or do you know if they use different ones for you?
They use those variables.
These are the exact ones,
Yeah.
A, B, H, and K?
Yeah.
Good. Okay. These have to do with moving a function in certain directions. So what you're going to find out, actually, let's color code them so that you know which way to go with which. K we'll do in red, and H we'll do in blue. Okay. Now, A deals with stretching and compressing. Okay. So if A is greater than 1, you're going to have what's called a vertical stretch. Okay? So if this A here has a number that's greater than 1, that means we're going to vertically stretch the graph, whatever it is. Now, right now, we've only done with parabolas, but you're going to start to get into all different kinds of functions, and you're going to be talking about stretching them. If A is between 0 and 1, you're going to get a vertical compression. Okay? And what these is, they're showing you shortcuts. Because remember how we did on the page before, where we had this, and we're plugging numbers in? I could do that for any function. No matter what they give me, they could give me a very elaborate one, I could constantly do this. The only thing is it takes a very long time, especially to fill out a large graph. So what they're doing now is they're showing you how these stand for numbers. Numbers in these specific slots, if they're in there, how they'll change a graph, so we can go to the parent graph and change it from there. I know I said a lot, so we'll keep going with this. And finally, if A is negative, so I'm going to say if A is negative, the graph is reflected on the x-axis. Okay. Have you ever seen anything? Okay. Now, B is the same idea. Okay. The only thing is, B deals with horizontal. Let's put these little things in place. A is going to deal with up and down, vertical, and so is K. That's why I did them both red. Okay. B is going to do horizontal movements, and H will do with horizontally affecting the graph. Okay. A and B specifically are stretching and compressions. H and K are movements of the entire function. Okay. So if we have B and say B is greater than 1, the only thing about B is it's the opposite idea of A. So when A was greater than 1, we got a vertical stretch. When B is greater than 1, we're actually going to get a horizontal compression. Okay? So in other words, A and B have kind of the opposite effects. Now they do one does up and down, one does left to right, but when A is greater than 1, it's vertically stretched. When B is greater than 1, it's horizontally compressed. Okay? So using that same logic, if B is between the numbers 1 and 0, it would be horizontally what?
Stretch.
Ah, good. And finally, if b is negative, do you know what would happen here? It'd still be reflected.
On the y-axis.
Good. Reflected on the y-axis. Is this all old news to you?
No.
No? It's good to go over? Okay. Next thing, I'm going to work with k. Okay? The letter k, and I know I'm only using variables right now, but we're going to get into numbers. I'm going to show you exactly how it affects these things. Okay? So if k is positive, okay, that means we're going to move the entire function up. Okay? So we move the whole function upwards, or in a positive direction is a way of saying it. Okay? If k is negative, we're going to move the entire function, or whatever the graph is, down, or in a negative direction. Does that make sense? It makes sense because positive, you think going upwards, negative, you think downwards, just like a temperature, right? So k is intuitive, in other words. It makes logical sense. Now, just like b with a, h has the opposite effect. So if h is positive, we're going to move left. Okay? What direction is left on a graph? Do you know? If it's going to be, remember I said before, well, k only deals with up and down, and h deals with left and right. We talked about positive direction. Moving left on a graph, do you know what direction that is? Positive or negative?
Negative.
Negative, that's right. So when h is positive, we move in a negative direction. Okay, it's counterintuitive again. It does the opposite of what we would think it would do. And if h was negative, we're moving right. Okay, but right is in what direction? Positive direction. Okay, does that kind of make sense?
Yeah.
Let's take a look at this. And I know we covered quite a bit there. These are kind of the rules of a function. And you said you've seen something laid out like that before? Okay. So we're going to go into actually applying these into functions and how those movements will look, okay? Okay. Okay. So now, say we have a function. Here's our graph. Okay. Like I told you before, we're working in function notation, which you said you're familiar with. So we have f at x is equal to, one of the functions that can be equal to f at x is equal to x. Okay, that's a linear function again, okay? L-I-N-E-A-R. This is a linear function. F at x is equal to x squared is quadratic. Okay. Have you done anything else? For instance, have you done f at x is equal to the root of x, maybe?
Oh, no.
Nope.
We've done, like, formulas and just fill in what x is.
Yeah, okay, yeah. You've definitely done those. Okay, that's good. Let's talk about moving, because you're going to get into moving these functions very soon in your course, okay? When we talk about moving things, remember we had all those letters involved. You're going to have to apply these f at x functions, okay? So eventually you're going to get into, they're going to say f at x is equal to, and, you know, they're going to put the number maybe 3 x minus, let's say, 2 squared. I'm just making this up as we go. Plus, let's say, 4. Okay? So first of all, I want to see, can you match this to the parent functions? These are both parent functions. Okay? In other words, considered originals. These are the original, and then we would be making movements from them. This is the linear parent function. This is the quadratic parent function. They use the word parent. You can think of them as the originals or however you like. Do you know what this is a change of, a variation of? Which parent function?
Quadratic.
Yeah, that's right. Because we have the squared in here, we're talking about this parent function here. So quickly what I'm going to do, again, are you okay if I just do these numbers, or do you want me to number all of them? You sure?
Yeah.
I can number all of them.
No, that's all right.
That's all right? Okay. So these all stand for 1. I'm going to draw the parent function to start. Okay? And if you remember a parent function, do you remember where the vertex goes? Did a little earlier.
Starts at 0.
Yeah. And then I would go over 1.
And up 1.
Yeah. And we'll go over 1 the other way. I'd go
Up 1.
Yeah. And if I go over 2?
Down 4.
Good. Okay. Over 2 the other way.
4.
And over 3?
And 9.
Yes. And 9. So this is our parent function on a graph. We've seen it, okay? Oh gosh. Not the best at connecting the dots, but does that make sense? Okay, so there's our parent function. Now what I'm going to need to do is I'm going to need to relate these. First of all, let's try to figure out what letters these correspond to. And I'm going to draw, the word I use is a skeleton model, but if that doesn't help you, don't use that obviously. But let's do it like this. Plus, okay, I'm going to put the letters in here. We have A, B, H, almost put it in. Okay. So remember I talked about these are all the different types of, these are all the possible movements you can have. There are really no more than these, okay? These numbers I've now placed into this function, right? This was the original. I've now placed numbers in. Do you know which letters or variables they represent these numbers here? What would 3 represent? A, yeah. Luckily I've color-coded this, so I've made it very simple for you, right? But we'll get a little harder as we go along. So there's A. What would -2 represent?
8.
Yeah. And 4?
Okay.
Good. So I didn't put a B function in, okay? And actually you're going to learn that B doesn't, we'll get into that. It doesn't really affect the quadrilateral. It affects other ones more. Anyways, so from what we've learned is H and K deal with movements. So here's my original parabola. This is our original parabola. Let's talk about a movement of K first. We're going to do these one movement at a time. If K is positive 4, what do I do with this entire parabola? You remember?
Move it up.
Move it up. So every single point is going to be moved up 4. So the vertex goes up 1, 2, 3, 4. So here's my new vertex, and I'll do it in red, okay? Now from there I can move each point up 4, or, because I haven't made any changes, I can just redraw the parabola. Personally, I like just redrawing the parabola, but if you want to move every point up 4 at a time, that's fine. Because I'm so used to writing it out over 1 up 1, over 1 up 1, over 2 up 1, 2, 3, 4, I just find it simpler than going to every point, okay? So the shape of this parabola is actually the exact same, okay? All that's happened is gone up 4. Remember that was our positive 4, which is our K. So I moved it up 4. So here's one of, looks like 3 steps, okay? Now let's talk about H next. What is H? What number is it?
2.
Not just 2, but
Oh,
negative 2, okay? If it's negative 2, which direction do I move? Do you remember?
Left.
It's counterintuitive. So left is a negative direction, you're right. Remember, H is counterintuitive. So if it's negative 2, which way would I go?
Positive.
Yeah, I go in the positive direction. So I'm going to go over 2, okay? So my new vertex, we'll do it in blue, actually is going to be 1, 2, 2 over, okay? So here's the next step. Again, I can move each point over 2, or I can just redraw the parabola. In terms of what's going to work best for you, I actually think if you learn to just continuously redraw the parabola, it'll be more beneficial to you, okay? So here's my vertex, over 1, up 1. Does that make sense?
Yeah.
Okay. Over 2, up 1, 2, 3, 4. 4. Okay, and obviously I can't fit the 9 on here. So again, it's the same shape. The only difference is this parabola is now up 4 units. It's been shifted. Negative 2 is our H. It's been shifted to the right 2 units. Okay? So that's where our new parabola is. When you go to draw this, okay, and we're not done, we still have to do with 3. But when you go to draw this, you don't technically have to do the original, then the first movement, then the second movement. I'm putting them all together, just step by step, okay? So that it makes sense to you. Finally, this is the difficult one. A. A deals with stretches and compressions, okay? So one way to put this is whatever your parabola is, A will not affect the vertex. H and K affect vertexes. You're going to learn A and B, they don't affect it. The vertex is always going to stay in the same spot. no matter what these numbers are. It's only when h and k have numbers that the vertex is going to move. Okay? So that means now that I've dealt with my h and my k, the only thing left is to work on my a, which is 3. My vertex is going to be the same. I'll do the final one in green, okay? Just because I know it's getting a little clouded in there. My vertex is still going to be here. The only difference is now, when I go over 1, normally I go what? Up how many? 1. Take that number 1 and multiply it by a. Okay? So I go over 1. How many will I go up now?
3.
Yeah, 1, 2, 3. Okay? I go to the left 1. How many should I go up?
3.
Yes. Okay. What about when I go over 2? When I go over 2, normally I go up how many?
6.
Normally, if I go over 2, how many do I go up? I'd square that. 4. And then I multiply 4 times 12. Yeah, so it's going to be way up there, okay? So in other words, you know what? I'm going to estimate it's here, okay? I know it kind of runs into the other ones, but if you notice, the whole reason I drew this very, very high is the way they're trying to describe this is this has been vertically stretched. Think of it like an elastic band, right? A was greater than 1, so that means it's been stretched. So it's been pulled like an elastic band and gets thinner and thinner, okay? I know sometimes it gets confusing because you think compression would make it in and then wider would be out, but the words they use in math is this is a stretch when it gets thinner, and when it gets fatter or wider, that's considered a compression, or at least vertically, okay? So does that make sense? So I'm going to actually redraw the final one, just down here. There we go. There we go. So the final one, let's put our numbers down again. 10, 10, negative 10, negative 10. I'm just going to go look. Remember, my new vertex was at 2 and 4. That's my new vertex, so I'll do it in black, okay? So my new vertex, I went over 2, up 4. And that makes sense because our h and k's were the numbers 2 and 4. Let's get a real vertex. That makes sense? Okay. And instead of going over 1, up 1, I went over 1 and up
12.
Well, if I went over 2, I was going up 12. I go over 1.
3.
I know I can't fit the rest, so we have a parabola that's going like this. Okay, so this is our parabola. If you're going to graph that function, technically this is all you would have to graph. Okay, but I decided to show you every step involved. Okay, just so it makes sense. So technically we did 1, 2, 3 different things for that parabola. Okay, does that kind of make sense?
Yeah.
Okay. Okay, now let's talk about domain range. What they've given us are coordinates. And we're actually going to go ahead and plot these, okay? Same numbers we used before. 10, 10, negative 10, and negative 10. Okay? The first point, 1 and 3. I'd go over 1, up 3. That's our first point. Easy? Okay, good. 2 and 6. Over 2, up 6. 4, 5, 6. Simple? Okay, I'll speed through the next two. Over 1, 2, 3, up 2. Over 4, up 8. They give me 4 points. Okay. Now, have you talked about whether something is or is not a function yet?
Yes.
Have you heard of a vertical line test?
Yes. Yeah. Basically, see how many points are in the line.
Yeah, exactly. So, if I draw a straight line up and down, that wasn't that straight. Does this touch more than 1 point? No. What about a vertical line here? Does it touch more than 1 point? Here?
Yeah.
It touches more than 1 point?
No.
No. And what about this one?
No.
No. So if a vertical line, no matter where we are, only touches 1 point, that means it is a function. So first of all, if they'd ask us, is this a function? We would say yes. So A, let's say yes, this is a function. And the reason it is a function is because it passed the vertical line test. I'll just put a little note. Passed vertical line test. Okay, so now that I have that, now they're going to ask us about domain and range. Do you know which of the accesses domain deals with?
X.
That's right. Domain deals with X, therefore range deals with
Y.
Y. Good, good. So, have you done the notation for domain and range?
I think so.
They give you a D and a semicolon. Have you seen that before?
Yeah.
It'd be kind of like
Oh, yeah, yeah.
yeah? Okay. Now, and I'm going to do a range here. Okay. Now, I bet you've probably seen this. Maybe you don't even remember it. Maybe you do.
Yeah.
You seen that?
Right.
Okay. Right now we're doing basic domain and range, so actually we don't use this to start. I'm going to show you when we're going to use that, okay? I just want to make sure there's some kind of connection. So, since domain deals with our x values, what are my x values here?
1, 2, 3, and 4.
Real simple. So, my domain of the function is 1, 2, 3, and 4. That's my domain. What about my range? What are my y values?
3, 6, 2, and 8.
Okay. Now, I'm going to try to put them in order. So, the lowest number was 2, then 3, then 6, then 8. So, the domain of this function is 1, 2, 3, 4, and the range is 2, 3, 6, and 8. Mainly because this is not a continuous function. Okay? Had this been something like that, very different. But because we only had 4 points, that's the domain of 4 points, and that's the range of 4 points. Is that okay? Okay. Let's go into how different this would be now. So we'll do it in red. If this was called a continuous function. Okay? Let's say we had this as a graph. That was it. Okay. Now, this is where we're going to get into what we had before, the XER, and we're going to do YER. Okay? So let's actually start with that. If it ever becomes continuous, instantly I know I have to use XER and YER. And the reason is because every single point in here, I don't want to have to write all those numbers. Not only do I want to, it's actually infinite. Because I could write 1.1, 1.2, 1.3, 1.33, 1.334. Like there's so many numbers we can write. So we're using a symbol to represent everything. Okay? So let's talk about the domain of that function. We'll do it in red. Our domain is XER, and our range is Y. And this stands for the element of all real numbers, is what it means, okay? Element is every real number. But the only thing is, does this function go on forever? No. Does it have a starting point?
Yes.
And an ending point?
Yeah.
Good. Let's talk about its horizontal starting and ending points. So how would it be dealt with on the x-axis? What would one of the starting points be?
1 and 3.
Yeah, 1 and 3. So on the x-axis, its starting point is 1. And what's its ending point?
4 and 8.
Okay. And on the x-axis, its ending point is 4. Okay, so I'm focusing just on the x values. Okay, so when x was 1 and 4. So it exists between those 2 points. Okay, so in other words, what I'm going to say on the restrictions is x is every number, I put a line down here, between the numbers 1, so I put less than and equal to, greater than and equal to, less than and equal to 4. So what I'm saying is x is every number between the numbers 1 and 4 on the x-axis. Does that make sense? Yeah? Okay. What about range?
Range is 3 to 8.
What's the lowest point of the range? You think it's 3?
2.
That would be 3. Is that the lowest point? No. What is it?
2.
Yes. Here's our lowest point. So there's our range, and what's the highest point?
8.
8. Okay. If you'll notice, I've encompassed this function into a box. Technically, every function can go into a box. Okay. Just as long as it has ending and beginning points. Some functions have arrows, things they go on forever, so then they don't have restrictions in a sense. So what are our restrictions on the range? We go as low as what number?
2.
And as high as 8. So now what we're going to say down here is that y is every real number between the numbers 2, and we use y, and
8. So when the numbers are negative, right? It's, for example, it was -2. It'd be -2 is less than y.
We just have to make sure that we put y is between them. I could have rewritten this, and I'll show you again another way we could write this range. Y is all real numbers. The restriction, I could have had 8 here, pointing this way at y, and 2. Okay? Depends what number you want to start with on which way these are going to go. Do you remember that little trick when in elementary school, maybe like the bigger guy's pointing at the smaller guy? Did you ever, or the little guy's eating the bigger guy when making greater or lesser signs? No one ever showed you that trick?
Oh, yeah.
Okay. When you're doing that, essentially you just kind of try to think of it like that when you're setting it up, because this is technically called greater than, right? And this is technically called less than, okay? So really this says y is every real number such that 2 is less than and equal to y, and y is less than and equal to 8. That's a lot to be said. It makes more sense if you just kind of look at it and you go, y is between the numbers 2 and 8. Okay? Always make sure the big guy is pointing at the littler guy. So in this sense, y is bigger than 2. We know that, right? Because this is its lowest point, and it exists all the way up here. So I know y is bigger. So y is pointing down at 2. But we also know that 8 is the highest. Y doesn't exist up here. So 8 is the bigger guy. So 8 is pointing at y. Okay. This is also acceptable. See how I start with the number 8 and then end it with 2? As long as the signs will be the other way. Does that make sense?